So, Elaine, you asked me to talk about. You sent a thing. You sent a thing to me. You always send little things in your email, and sometimes I talk about them, and sometimes I won't. And I won't talk about it this time either. But I will tell you what it is you said, and I'll tell you the answer, my response to it. Elaine said, "See, everybody knows that everything we are made of, all the good stuff that we're made of, besides the hydrogen, which sort of comes free from the universe, everything else that's in our bodies was made inside of a star. So everybody knows that in this room. And then everybody in this room knows that that was made in a supernova. Okay? So everybody knows that in this room. And so what was in today's Times was that maybe that's not quite true. Okay, so to respond to the thing that the New York Times said, turns out that while supernovas make all the good stuff that you have in this room, they're not good enough to do it all. And apparently, if you look among the supernovas in the world, there are a few that do an unusually amazing thing compared to the rest of them. Some supernovas just simply are a star that is a little too big, and at some point it can't hold itself up, and it implodes and explodes, and that's a supernova, simply. Then there are supernovas that are so big that the star is ginormous, and when it explodes, it does, not only does it make a little black hole at the center, but it seems to blow up more stuff than the rest of the supernovas in the universe combined. So one supernova that is a giant star blowing up can more than make 100 times the amount of us that the nearby supernovas have to offer. That's what the article said. And to some extent, I believe that, because it's in recent conversation. So I've read a few conversations about that. So it seems to me that it's getting closer to being an acceptable thing, rather than the thing that everybody else says, which is it's supernovas all the way. In this case, it's giant supernovas most of the way, and then it's little itty bitty supernovas around the time, because supernovas go off all the time in our universe, in our galaxy, like maybe one every 100 years, which would seem like a lot, except that we haven't seen any in our galaxy in 400 years. So if you're very, very poor at statistics, then you will think that we're overdue for one.
We're overdue for 4.
What?
We're overdue for 4.
We're overdue for 4. If you're really that poor in statistics, you'll think that we're overdue for 4, of course. But there's no way the statistics works like that, okay? It's not like if you're flipping a coin and you get a head and a head and a head and a head. You're not overdue for tail. Yeah. No, right? So the fact that we haven't had a supernova in 400 years worth a damn doesn't mean that there's going to be one next week for sure. I would like to see one in my lifetime. But what?
I maybe not.
Well, it could be real close, and that could kill us. Yes.
I sent you another one today, but I just want to tell everybody on your phone is something called the Medium Daily Digest.
Right.
And they're all articles on science.
Right. So the Medium Daily Digest, turns out that while they really give you some good stuff, after a while they say, you know what? I think you've had enough. From now on, I think you should pay.
I am?
Yeah, and I was paying.
So what is the paywall?
What?
How much is the paywall?
$50 a year.
15 a year?
$50 a year.
$50 a year. So what I did instead is there's this guy, Ethan Siegel, who you also introduced me to, and he is the guy whose articles are the most interesting in the Medium. So instead, I went directly to Ethan Siegel, and I give him $10 a month. So for him, I'm giving $120 a year, because he is this weird guy who writes great stuff, and I quote his stuff all the time.
Well, what I sent you today is about multiverse.
Multiverse.
Which I'm sure
I didn't get multiverse yet. We'll have to wait on that till
I
next
sent
week.
it to you.
I'll look at it next week.
What's Siegel's first name?
Ethan.
Ethan.
Ethan Siegel.
And it's a bargain, $50 a year.
Well,
and you
that's
get-
$50 a year for for Medium, which covers all of science, and Ethan Siegel, who goes down the rabbit hole of just physics and mostly astrophysics. So that's
Yeah, well, what they have here is mostly that,
yeah.
but it's fascinating and rather
Wait, let me see. Did I get it from you today?
multiverse.
Yeah, no. Okay, so let's go on. Okay, so the topic has been and always continues to be the Big Bang, because every time that I get close to the Big Bang, there's more stuff that I have to tell you that isn't about the topic that brought me to this in the first place. The topic that brought me to this in the first place is the idea that there's a problem with the Big Bang. Hold on, my phone is doing a weird thing. Why does it do that? I just turned off cellular and it's still giving me messages. There's a problem with the Big Bang, and I guess because I've been holding out for such a long time, I think it's reasonable for me at this point to get rid of this thing that I've been holding over the class's head for a long time. Although the proportion of people in this room that heard the story before is in the neighborhood of 40%. So 40% of you have heard the fact that I've been holding out on you, and the 60% of you haven't heard that I've been doing that to you. So, because in fact this class continues to be a group of people who drop in because Laird's talking about something today. Let's see what he's talking about. Today I'm talking about the thing that I didn't talk about for the last 3 weeks, and it's a simple thing. But it's terrific. It was, in fact, the impetus for me talking about the Big Bang in the first place. Because there's so much that I have to talk about before I talk about the Big Bang, that for me to go to the Big Bang is presumptuous, assuming you know the rest of the universe. Hey, you know the rest of the universe, fine, now we'll talk about the Big Bang. I really have to talk about the rest of the universe. But if I keep holding that out, we'll never get there. So this is the story. In the annals of astronomy, there have been, from time to time, little things that go wrong in the data. And you look at the data and you go, oh, I think I understand that. And then you look at it more closely and then it looks a little bit suspicious. But you think, oh, it's probably because I made an error in my measurements. And then you look at it more carefully, and the more carefully you look at it, the error begins to go away, and now you have data that tells you that something is wrong with the way you think about the universe, and you better do something about it to fix it. For example, one of those errors was what they call the precession of the planet Mercury's orbit. Mercury goes around the sun once every 88 days or something like that, and its orbit comes in close and far away, in close and far away, and you would think it would do that forever, and it does do that forever, but it doesn't do just this forever. It does this, and then it keeps changing the direction where its low point is towards the sun, and that's called the precession of the orbit of Mercury. And the precession of the orbit of Mercury precesses. It still does the 88 days, but it precesses around the sun, so its low point, side point move. That precession is 560 arc seconds per century, which is a measurable quantity. You can see it even with the telescopes that existed at the beginning of the 20th century. You could see it. It moved. You would have to look for years and years and years, but you could measure, oh, it's moving. The orbit is precessing. Let's figure out why. They sat around, they figured out why using the best computers they had in those days, which is in the 1920s. Those computers were called human beings, and the human beings figured out why the orbit of Mercury precessed. And they figured out that it precessed because Jupiter was pulling on Mercury. And the Earth was pulling on Mercury, and Venus was pulling on Mercury. And so they figured out how, and the sun isn't completely round. They figured out all the things that would explain the precession of the orbit of the planet Mercury, and they came up with something like 30 out of 500 short. They couldn't explain 30 arc seconds of the 500 arc seconds that it was precessing. 30. And you think, well, that's okay, it's close. But it wasn't close. It was below the errors. The errors said we don't have errors of 30, we have errors of 3. So where do you get 30? You got to account for 30. Guess who accounted for 30? Einstein. Okay? Einstein's theory of general relativity accounted for this very small discrepancy. So out of little discrepancies come big theories. The fact that the orbits of the stars around the center of galaxies seems to go around too fast, and that just doesn't seem to be enough matter in the center of a galaxy to keep those stars constrained and not flying off into the distance. Those stars should fly off to the distance, and how come they don't do that? That's a little thing called dark matter. Okay, dark matter, little problem in the data, gives you dark matter. Yes.
Do not all the planets then have precessions? If Mercury has it, shouldn't Earth?
All the
and Venus?
planets have precessions.
So it's just the interaction of the gravitational pull, large as that
Yes.
may be, or small as that may be, on each other.
Right. The orbits of all the planets in our solar system change over time due to the influence of all the other planets in the solar system. And they're measurable and predictable, and we know what they are, and they're small compared to the precession of the planet Mercury. But even the Earth precesses by a small amount, an amount small enough that nobody that I know has ever talked about it. But if you could find a paper somewhere telling you about the precession of the orbit of the planet Earth, it does precess.
And is it because Mercury is one closest to the sun,
It's because
and
it's-
two, a small planet,
And,
that it
and
precesses
third,
more?
it's the most eccentric orbit. Its orbit is eccentric,
Right.
so it really does a big number in terms of weaving in and out. So that precession is more observable. So dark matter was another thing that they discovered in the data when they couldn't explain all the data. A third thing that they couldn't explain, little noise. They had this radio telescope trained on the heavens, and they had all this superfluous noise that they were getting, and while they tried to clean the radio telescope and fix all the wired connections and do everything, they still had this noise. And the noise they couldn't get rid of it. And now, of course, we know that noise happened to be the Big Bang. Okay, so little things that you just pick up on the sidelines turn out sometimes to be the biggest deal. So, gotta find my water. So what did they just pick up on the sidelines? Well, look, here's some data, okay? Data over here in blue, data over here in red. The blue data, the data point is indicated by a dot. The error in the data point is indicated by a line. See the line? See the line? See the line? This is one piece of data, and this is other data measuring the exact same thing. And this data also has error bars,
But much larger.
larger error bars, but notice that the error bars of this do not intersect with the error bars of this. So it's either this is right and this is wrong, or this is wrong and this is right. But they both can't be right. Measuring the same thing, they both can't be right. And what is the thing they're measuring? They're measuring the expansion of the universe. They're measuring the rate at which the universe expands. And the difference between these two is this is done by Team A, and this is done by Team B, and they use completely different methods that have nothing in common with each other. So each of these can be believed on its own merits. It's just that they don't agree with each other. And the reason it's interesting now is because these error bars, as you see them now, used to intersect. These error bars were bigger, and these error bars were bigger. So that they merged like this, and they overlapped. So people were comfortable with the fact that they overlapped, and so the answer clearly was somewhere in the middle, even if the data points were on either side. But then as the error bars got smaller, and smaller, and the technology got better and better, the error bars got smaller, and now we are left with a problem. What's going on here? Does this say something that we need to know about the universe? This problem has been coming for the last few years. The problem is, each time the error bars get smaller, people get more and more serious about trying to explain it. To the point where now people are at the point of saying, how do you explain this? But let's first of all talk about what it is that they're explaining. Okay? And that, so the answer, how do you explain this, is not, in my opinion, the interesting thing about this lecture. Because if I tell you 10 loosey-goosey reasons why this might be real and how to explain these differences, they're all loosey-goosey explanations. Nothing that I could tell you in this lecture could explain this. This is a mystery, of which the answer, bottom line answer is, maybe there's some new physics, is the bottom line answer. And then you go down the rabbit hole of what are the new physics, which I am really basically not going to go down. I might go down it for a little bit, another time, maybe today, who knows. But the point is, the controversy itself, the reason why there are these two different sets of measurements, is what's interesting here. So let's talk about this. The blue team, okay, is talking about the early universe as measured right after the Big Bang. So you look up in the sky, there's Big Bang, light coming from the Big Bang from there, and there's light coming from the Big Bang from there, and from everywhere there's light coming from the Big Bang. Of course, it's not called light, we call it radio waves, and those radio waves are what we see when we look at the cosmic microwave background, which I will show you a picture of here. This is good. Everywhere you look in the sky, I've not shown it to you this way before. Everywhere you look in the sky is a round ball around us. So in this case, I'm showing it to you like a round ball. There is radio waves coming at us. Some of those radio waves are cooler than others, and those are the ones colored blue. Some of the radio waves that are coming at us are red. Those are the ones that are warmer. Those are colored red. And the difference between the temperatures between the blues and the reds is in the sixth decimal place of the number. If the number is 3, it's 3.00001, or 2.99999 is the difference between the red and the blue. Just amplified for your enjoyment. Yes?
We're sending out radio waves.
We're sending out radio waves.
Now, if from a distance, looking at them,
Right.
would they have different frequencies of cold and warm as well? Where would they be on the spectrum?
First of all, we're sending out radio waves. We're intelligent. We tend to send out pictures. We have more pornography in our radio waves than probably anything else. Okay, so there's probably more porn out there being spread out to the universe than anything else. Okay, and probably a lot more things that you don't want to see. Very intelligent pictures, which have nothing to do with the very unintelligent pictures that are being sent out by the early universe. The fact that our pictures are in so many ways the product of our intelligence means that to compare our apple with that orange is really wrong. We are not a black body. It is a black body. We are only in certain frequencies. This is in all frequencies. There's so many ways in which there's nothing to talk about in terms of comparing. The only difference is we send out radio, it sends out radio. We're minuscule, it's the universe. So yeah.
It seems to me, I'm still mulling over the fact that you said it's a mystery, but you have two periodicities. You have two data sets, or one data set, that we do not have the entire data set.
Yes, we
So
do.
Do we? Do
Yes.
scientists think they have the entire data set
Yes.
on both those instances?
Oh, I'm sorry, which the second instance is? The
Well,
one,
the
the
blue
one
and
that
the
Barbara
red,
was
that's-
talking about, I was talking about the stuff that comes from Earth? Because that's not one of the data sets.
No,
I'm only
I'm
talking
not
about one
talking
data
about
set.
that. No, I'm
You're
talking about-
you're talking about those two things.
The prior ones,
No, the
yes.
prior one I was talking about two data sets. I'm talking about the blue data set now. Only the blue data set. The blue data set is the only one that on the left. The one on the right I haven't discussed. I will discuss later. It's called the cosmic distance ladder, and it has absolutely nothing to do with what I have on the screen right now. Absolutely nothing to do with it. Okay? This is just the Big Bang. The Big Bang, as shown by the picture, this is a snapshot of the Big Bang as it looks now when we look in the sky. You take tomorrow, the Big Bang will look the same as this, and every day, a billion years into the future, more or less, the Big Bang will look like this to us, to our eyes. It's an area filled with blues and reds and greens. In that proportion, in those places, it doesn't change. It's the universe as it's constituted now. Except it's a baby picture of the universe taken around 380,000 years after the Big Bang went boom. So it's not the Big Bang at the moment of birth, it's the universe 380,000, not million, 380,000 years after the Big Bang. And they know that number because they're very smart. The number changes from time to time, whether it's 400,000, 500,000, 380,000, but it's nevertheless, this is the baby picture of the universe. We're not exactly sure if it's the first day, or the second day, or the third day of the universe, but it's the universe when it began. And let's see what we can see in this universe, okay? This universe, you would say, well, gee, this is interesting. What can I possibly think about this picture? What does it tell me? And if you are not a scientist, and you happen not to be a cosmologist, and you happen to have not taken, something like 8 years of graduate school, then you may not be able to understand what this thing is. But I will help you skip the 8 years of graduate school that you need to understand this, and we'll go right to what this means. Notice that there are blues and reds. Notice that, let's look at the blues, for example. There seems to be a big concentration of blue here, and there doesn't seem to be many other concentrations of blue as big as this one. But if I look at a smaller concentration of blue, I can see that, well, there's a concentration of blue that is more or less the same size as this one, more or less the same size as this one, and maybe more or less the same size as this one. So there's more concentrations of smaller concentrations of blue. Let me look at smaller concentrations of blue. Well, how about this size? Well, if I look at blues in this size, there's all over the place, there's little concentrations of blue of that size. You see, frequency of the smaller blues is much higher than the frequency of the large blues. You can see that, right? You can see that that's a true statement about this picture. What happens if there was a theory that asked the question, what is the frequency distribution of the blues and the reds in this picture? And what happens if somebody came together and said, I have an idea, I have a theoretical idea as to what that concentration should be based upon a theory that I have. Let's see somebody look at that and see if they can show you what I just said in a movie. Okay, now here's a movie that does exactly what I just said. There's no sound, there's no talking person, but what it is going to do is it's going to show you the cosmic microwave background radiation. It's going to show it to you, and it's going to calculate a power spectrum, which is what I was just talking about, of the temperature fluctuations. This is the universe, the power fluctuations, just the big ones, like this. And they put a data point right here, right there. Then they do the power fluctuations of smaller units of things, and they put the data point right here. in red. Then they do even smaller fluctuations, and they put the data point up here. There. And then they do it again. So all they do is they go over the same picture again and again and measure the power fluctuations in different sizes. And then they come up with a graph like that that shows you the power fluctuations of the light from the Big Bang. Okay? There's the graph being made for you in front of your very eyes. That's the graph of the Big Bang as analyzed into a power spectrum that gives, there's the Big Bang, there's the colors, there's the power spectrum of the Big Bang. Now, and this has got to get you really ripped, because it gets me really ripped. Now, there's that power spectrum again, okay? This is the Big Bang, and you have to know that this particular picture that you're seeing of the Big Bang is not the best one. The best one came years later. So they had three satellites that did pictures of the Big Bang. First one, which could only see like this, and then the second one, which could see like this, and then the third one, which could see like down the tube of a straw. And it could look around the entire sky, and it did it, and it's still doing it. It was looking around the sky, and it's literally measuring that Big Bang picture for crazy and getting a beautiful picture of it, because you need the beautiful picture. Yes?
I'm not sure how to ask this thing in my mind, but when we look at that, it's more than one color, which means
It's more than one color.
more than one thing, whatever it is, power, whatever it is.
We're looking at colors.
Color.
Colors.
Whatever it is, it's not uniform.
It's not uniform.
all blue.
Whole point. It's blue and green and red and orange, yes.
Now, is that because this is so soon after the Big Bang?
No, it's because those are the difference in temperature. It's
Well, what causes the difference?
what causes the difference in temperature is the quantum fluctuations in the thing that made the Big Bang in the first place. When the Big Bang was banging, there were small differences.
It's not from one little thing. It's from a variety of things that would cause a fluctuation.
Yes, the fluctuations.
Big Bang comes from a tiny little dot of something, or not a dot, that's originally made of more than one type of thing to make it come out as more than one type of thing.
Okay, so the question you're asking, which is not, I don't want to dismiss it, but it's important. You're asking why the different colors in the first place. Why the different colors in the first place. And let me dismiss it and then discuss it later, at another time necessarily. The reason the different colors in the first place is because when the universe was very, very young, much younger than this, there were differences, little differences. The big differences between here and here got settled. They all got to decide on to be the same temperature. That was the big difference. But in the big difference, there were little differences that were still not smoothed out. This little difference didn't get to talk to this little difference and make a decision that they should all join up and become the same. So there were fluctuations. Big differences got settled. They're all the same temperature. That's a big deal. The fact that there are small differences is another big deal, but not the, and that's what they're measuring here. The fact that there are fluctuations in the first place. What is the spectrum of the fluctuations is the question. You're asking why the fluctuations. Good question, we're going to leave it alone. Just say quantum fluctuations for right now. Okay, it should be a good enough answer right now, but if it's not, we'll talk more. Yes?
Isn't there a possibility that there are cooling variations?
There are, isn't it a possibility?
The universe is large enough to accommodate a multiplicity of cooling variations?
Isn't
so
it
that
possible
accounts
there
for
are
the color
cooling variations? No, in this case, but the whole point of this is it's a good question, is not that there are cooling variations, because in fact, the universe is at one temperature everywhere.
You said
Okay,
that, yeah.
it's one. Well, that's the crazy part. That's great. It demands an explanation. It really demands an explanation, different from the explanation of quantum fluctuations. You're saying is cooling variations. The thing is that at any given time, right now, right this very second, this very split second, there's a difference in temperature between the tip of your nose and 1 inch above your nose. And that, or not an inch, 2 atoms away from this spot on your nose, there's a different temperature a little bit above, and they're going to equilibrate in the next billionth of a second. But in that billionth of a second, there's going to be a difference. And if the universe then expands, right then when there's differences, this part of your nose and that part of your nose separate and never get to equilibrate. Okay? So there's always fluctuations in temperature that didn't have a chance to equilibrate, and that's what you're seeing here. The differences that didn't equilibrate. Okay? That's what's interesting. So what you do is you sit down with Einstein's theory of relativity, general relativity, and you add a couple of other very well-known phenomenon to the equations of general relativity, and you try to map this power spectrum, and this is your success at this point. This is what your model looks like based upon these 6 parameters. These 6 parameters are the atoms in the universe. What percent are they? Currently it's set at 100%. The atoms in the universe is set at 100%. Cold dark matter, which is currently set at 74%, that adds up to 170%, it's not so good. And then dark energy is set at 4%. So these are just random numbers. And then there's other things. The Hubble constant, the ionization redshift, and the spectral index. Okay, these are 6 parameters that you can vary independently, that each of which has an effect on this thing. And the interesting thing is that you can vary these things all over the place to see if you can match, to get this to match that, and you won't succeed unless you get them all right. So I'm going to vary them one at a time, okay? First of all, the atoms in the universe, that's wrong at 100%. It's not 100%. We now know it's more like, well, it's getting better. Look, the graph is changing. We know it's not 75%. We know it's not 22%. We know that the answer is more like 5%. But that didn't help. See, it's not so good, but I'm going to leave it at 5%. Cold dark matter. We know the answer to that these days is 25%. This graph is set at 75%. I'm going to move the cold dark matter down to about 25% from here. And we're doing a little better, but we're still not doing so well. Dark energy we know is really not small, like 4%. We know it's like 75%. So I'm going to move this slider all the way up to here. And we're doing better. It's starting to look good. But we have more to deal with. There's the Hubble constant. Now the Hubble constant is an entire lecture, okay? And basically, and we're going to, it really is an entire lecture, maybe 2 lectures. But for the purposes of matching this graph, I can't digress for 2 lectures. Instead, I'm going to tell you what it is and hope you understand. If something is close to us, then it's close to us. If it's farther away from us, then it's farther away from us. But it's also, because the universe is expanding, if something is far away from us, it's also going away from us. And if something is further away from us, it's going faster away from us. So the further away something is, the faster it's going away from us. That's what they figured out. That's what Hubble figured out. He got to have a telescope named after him because he figured that out. And he got a constant named after him called the Hubble constant. The Hubble constant tells you how fast things are moving away from you the further you go away from you, how much faster those things go. The Hubble constant was the thing that I was showing you on the graph. I was showing you on the graph, that graph was measuring only one thing. And it was measuring one thing with all those error bars. And that one thing it was measuring was the Hubble constant. And it came up with 2 different groupings, the blue grouping on your left and the red grouping on your right. And the blue grouping on your left came up with a number. I'm going to set this graph to that number. I'm going to set it to approximately 73. Now, in fact, this graph was made when the Hubble constant, according to this graph, was 73. Okay? The Hubble constant is not any longer 73, it's 67, according to this graph. But this graph was made a few years ago when those error bars overlapped. These error bars don't overlap, and so this number 73 happens to be wrong right now. But for the purposes of illustration, and then we're going to change the ionization redshift, and we're going to get to the answer and press the button for the answer. There is the answer. Hubble constant 73, ionization redshift 11, spectral index 95, atoms 4%, cold dark matter 22%, dark energy 74%, and look how well it matches. We have a match, folks. We have a model of the universe which we believe in our heart of hearts is true. And this model explains the data. And not only does it explain the data, but it gives you absolute numbers for what that data is, including the Hubble constant, which in this graph says 73, and if we did it again today, it would say 67. Yes?
If something, the farther away from us it is going faster, and that's not just perception,
It's reality. It's going faster the further you go away.
Faster. That means that at some point there will be a void or a space between what's out there and what's in.
Things are moving away from each other, and the galaxies are getting further apart. So if you...
eventually the outer part will be gone.
The outer part will be gone.
leaving something that is moved more slowly in the middle.
The thing in the middle is moving at an intermediate speed, because it's a space that's expanding. These objects are not moving. Space is expanding. It's the opposite of what you think. Einstein said you can't go faster than light. He's right. He never said you can't move the universe faster than light. You can take space, which is, what is space? And you can move space and make it bigger, any speed you like. Because there's nothing about space expanding. It's just light traveling faster than the speed of light in space. Doesn't seem to make sense. Anyway, space is expanding, and so there's nothing in between that's going to be left behind. It's just bigger space in between these objects. And that's the way the universe goes. That's the way it plays. Nothing's being created in the middle. When there was a thing called steady state theory of the universe, and that was an actual theory, then in that actual theory they also had atoms being created in the empty space between, because they didn't like the fact that otherwise the universe wouldn't be a steady state. So you had to have stuff being created in the middle to make up for the voids. Well, that's not the way the universe plays. It doesn't roll that way. Then nothing gets made in the middle. It just gets bigger. Yes?
To me, Kabbalistic, the Kabbalistic notions are something similar to this, but it sounds as if when I think about the expansion and endless expansion and the speed of the expansion being, again,
Faster than the speed of light.
That means that eventually there's going to be a huge middle of nothingness.
That's true. A big nothingness.
Big, huge nothingness.
You can look forward to it.
Getting bigger all the time.
Yeah, you can look forward to the nothingness getting bigger all the time.
Yes, sort of
Right.
like my life, yeah.
Yeah. But unfortunately, your life will be measured in factors of 10 to the second power, and the universe's life is measured in units of 10 to the 10th power of years and beyond. Right. So that the universe on the average lives at least 10 to the 8th times longer than you will. So there's 10 to the 8th of you can be fit into the remaining universe, or the universe that's previously existed. 10 to the 8th lifetimes of you, prior to you coming up with this idea. Okay. So just look. This is it. So I reset this thing. This is where it was, and I press the answer button, and I get this. Ta-da! The universe, cosmic microwave background analyzer. We know the answers to these questions, and one of them is the Hubble constant. Let me change the Hubble constant on you, okay? Just that, nothing else. And change the Hubble constant, and you can see when I change it to 84, it doesn't work. When I change it to this number, well, it doesn't stick at that number. Change it to this number, it doesn't work. This stuff is sensitive to the Hubble constant. Now let's go back to that graph. Let's go back to this graph. Okay, so what we've been doing, you see, is we have these error bars, but nowadays we have this error bar. In the past, I had the picture I was showing you allowed for. Well, the picture I was showing you allowed for 73. There were error bars this big previously, but now the error bars are this big, and that's 68 or 67, and this doesn't have anything to do with these. What's this? This is also a measure of the Hubble constant. What is this? Okay. So you need to know how big the universe is. And the universe is a big place, but how do you know that? In 1920, there was a debate with two prominent astronomers, Shapley on the one hand, Curtis on the other hand. 1920. They looked up in the sky. At that point, we had good telescopes. We looked up in the sky and we saw these spiral nebula in the sky. Andromeda, a galaxy, is a spiral nebula. All the galaxies you've ever seen pretty pictures of were talked about in those days as spiral nebula. We thought that those spiral nebula were inside of this thing called the Milky Way, which was the universe. And the spiral nebula lived inside of our universe of the Milky Way. And then it was discovered that maybe it's not inside, maybe it's outside. And there was a debate as to whether these guys were inside or outside the Milky Way. And it became one of the most famous debates in all of astronomy. The debate was in fact held. Nobody won that debate, but within the next year or two, the astronomical community settled on the answer and settled on that answer forevermore. And they decided that these things were outside. And Hubble, among himself and his predecessors, discovered exactly how far outside. And the way he did that was a way that we still use to this day. The first way you tell how far something is away is you look at it, okay, and then when the Earth goes to the other side of the sun, you look at it again. And I'm looking at the people in this room, and your head is to the left of her head. And now as I go over here, your head is to the right of her head. So you're moving, she's moving slower, you're moving faster as I move. And that effect of the movement of the things close moving faster than the things behind, that's called parallax. And that's simple to see. You just hold your finger out in front of your eye, close one eye, close the other eye, and your finger moves. And it moves in front of one thing and then the other. And so you see your finger move against the background objects that are behind me. I'll move as your finger stays stationary. The finger will move against the background stars. And you can then see on the basis of trigonometry, which you all learned in 10th or 11th grade, exactly how far each of you are from my finger based upon the trigonometry we learned in 10th grade, and which the ancients knew, and we certainly knew in the beginning of the 20th century. So we're able to figure out, based upon the Earth going around the sun, we could see an object like the Pleiades, which is a constellation in the sky. We can see it move against the background of the stars behind it. We can see it literally move. Yes?
To me, it seems like there's a gigantic joke here. the universe is expanding faster than the speed of light into itself, as we, who are mostly empty space, 99-point-something% empty space, observe it doing it. There's something really funny about that.
Well, I think it's very funny that you're on talking about it in the first place, because I certainly have no way of explaining my consciousness. What are you, what are you talking
I
about?
mean, isn't that funny?
It's funny that we get to talk about space, and we're mostly empty space. Yes, right. So listen. So what I think what I want to do is stop here